Hi everyone, I'm Tharma and I'll be presenting the work titled Space-Efficient Quantum Algorithms for Mode, Min-entropy and k-distinctness. This work was jointly done with Dr. Debajyoti Bera. In this work, we first defined a problem called the high-disk problem. Given a discrete probability distribution over endpoints, a threshold tau and a parameter epsilon, the problem is to report if there is any point x such that probability at the point x is at least tau, or if for all points x, probability of x is at most tau minus epsilon. We assume that promise that one of the cases is true. In a classical setting, assuming unbounded space, one can estimate the probability distribution in at most order 1 over epsilon squared queries. If the space is bounded to log n, then the best known classical algorithm uses order n by epsilon squared queries. However, we show in this work that if we were to use a quantum computer, we can answer the high-disk problem using log space and merely O tilde 1 over epsilon times square root of many queries, where O tilde hides some log factors. Notice that the query complexity in the quantum setting is actually independent of n. To do this, we construct a quantum algorithm in which we first initialize a quantum state such that the quantum state is in a superposition of all the points of x that are in the distribution, and for each of this basis state, the amplitude of the state is square root p of x, that is square root the probability of x. Next, using quantum amplitude estimation, we estimate the probability of each of these endpoints all in superposition with epsilon additive accuracy. Now this costs us order 1 over epsilon queries to the oracle. We then, in superposition again, compare the estimates against a value tau and use a coin register to actually mark the result of the comparison. If the estimate is greater than tau, then we flip the coin register to 1, else we set the coin register to be in 0. There was at least one point x such that p of x is at least tau, then on measuring the coin state at this point in the algorithm, we would obtain 1 as the measurement outcome with probability at least tau. And if there was no such x, then the probability of obtaining 1 on measuring the coin register would be 0. Using this, we perform the amplitude amplification on the coin register with the goal of obtaining the state 1. This is done using order 1 over square root of queries to the oracle. Finally, we measure the coins register and report true if the outcome measurement turns out to be 1, else we report as false. It is easy to see that if there is at least one point x such that p of x is greater than equal to tau, then we'll obtain 1 in the measurement register on measuring the coin register with probability close to 1. So this gives us an O tilde 1 over epsilon times square root tau query quantum algorithm. Now, since tau has to be at least epsilon, the worst case complexity of this algorithm can go as big as order 1 over epsilon to the power 3 by 2, but it still beats the best known classical algorithm. If tau was constant, then the quantum algorithm actually gives a quadratic speed up over the best known classical algorithm in terms of epsilon. Now we extend this high-disk problem to define another problem named the Pmax problem. In the Pmax problem, we are actually given an oracle for probability distribution, very similar to that of high-disk, and also an accuracy parameter epsilon. The goal of this problem is to obtain an epsilon approximate estimate of the largest probability of the distribution. Now we try to solve this problem by combining the algorithm for the high-disk problem, which we mentioned earlier, along with the classical binary search algorithm. And by this combination, we obtain a quantum algorithm with complexity O tilde 1 by epsilon to the power 3 by 2. We also give quantum algorithms for these problems where the accuracy parameters are not additive, but rather they are relative. In the next part of the work, using the above algorithms, we solve the problems of f infinity, k-distinctness, and min-entropy. Now, given an n-sized array of elements, the k-distinctness problem for a fixed k is to report if there is any element that occurs at least k many times in the array. The f infinity problem is to obtain the element that occurs the most number of times in the array and to return its frequency. The famous min-entropy problem is essentially to estimate the min-entropy of the given probability distribution with epsilon additive accuracy. We show that the k-distinctness problem can actually be reduced to high-dist problem. The f infinity problem can be reduced to the additive accuracy version of the Pmax problem, and the min-entropy problem can be reduced to the relative accuracy version of the Pmax problem. Now, using these reductions, we obtain quantum algorithms for these problems with query complexities as given here in the poster. As the final part of the work, we also derive lower bounds for these problems, and we show that our algorithms are almost optimal for all problems. And for certain special cases of these problems, our algorithms are actually query optimal. That is, you cannot get an algorithm with lower queries than our algorithm. This work opens up a lot of new avenues for the future research. These results demand a discussion on the space-time lower bounds of the mentioned problems, so as to see if algorithms with even lesser complexities are possible in the log space regime. We conjecture that the problems for the problems of high dist and Pmax, our algorithms are query optimal in the log space regime. Another direction of work that could be to investigate if these algorithms or some simple modifications of these can actually be used for similar problems in the streaming mode. In case you are interested in the intricacies and details of our work, you can obtain a full version of our paper in arXiv. Thank you.